Our agenda for this presentation is to talk about general IPv6 address auto-configuration technology, its behavior, how it works, take a little bit of a close look at the DHCPv6 protocol and how it works, and then talk about how we deploy DHCPv6 deployment considerations and how we configure this with if you had a Windows-based infrastructure. And then last, we'll take a look at the IPv6 Test Lab and how you can set this up for yourself and see the behaviors firsthand. Okay, so what is this stuff called IPv6 address auto-configuration? Before we get into the details of that, I'd like to take a step back and just briefly review what address auto-configuration means for IPv4. For IPv4, we have this well-known and trusted friend known as the Dynamic Host Configuration Protocol. This is a part and parcel of any enterprise or networking environment that allows hosts to wander from subnet to subnet and always get a relevant address and routing configuration for that subnet so that that their connectivity is not impaired. So address auto configuration for IPv4 means DHCP and a DHCP infrastructure. For Windows hosts, in the absence of a DHCP server or a DHCP relay agent on that subnet, that's relaying messages to a DHCP server, we have this automatic private IP addressing address, the 169.254. It's kind of a fallback position. If we're on a single subnet network without a DHCP capabilities, we at least have an address with which we can communicate. And you can consider a single subnet routerless and DHCP-less configuration to be, say, a wireless ad hoc network, for example. So in the absence of a DHCP server, Windows host will use an APIPA address at 169.254. And Windows hosts also have this notion of an alternate configuration. In the absence of a DHCP server, there's a static IP address configuration that they can fall back to. And this is in place so that I can have DHCP on my corporate network, and when I attach to my home network, I can have a custom static IP addressing configuration. So that's what it means for IPv4. So what does it mean for IPv6? Well, the first thing that we do as an IPv6 node is we configure what's called a link local address, and we always do this. So it's like we're doing the APIPA address, but it's not as a fallback position. It's really as a primary address to communicate on the local subnet. Once we've got a link local address, then we perform a process called router discovery, where we query the local subnet to see if there are any routers on that subnet and what information they have to offer us in terms of addressing and configuration. One of the things that we can get are what are called stateless addresses based on received messages from routers called router advertisements, or RAs, or if indicated by the routers, we can query DHCPv6 servers and get what are called stateful addresses. So the router discovery is that crucial process that tells us that there's routers on the local subnet, configures some configuration parameters, but also tells us whether we need to go to DHCP for additional information or addresses. Now, in the absence of a router advertisement, IPv6 hosts will fall back to DHCPv6. Now, imagine that single subnet, routerless, DHCP-less subnet configuration like a wireless ad hoc network. What happens in the IPv6 case is that we configure a link local address. We try to find a DHCP address, a DHCP server, none is found, but we still have the link local address as the equivalent to the APIPA address that we can do local subnet interactions by name or using that link local address. Okay, so let's talk a bit about the link local addresses themselves. Link local addresses are very distinct in the sense that they start with FE80::. The first 64 bits define the link local address prefix. And again, these are equivalent to these APIPA IPv4 addresses, but unlike APIPA, they're always configured as opposed to just as a fallback position from DHCP not being available. These addresses are crucial for on-link interaction and a whole set of processes known as neighbor discovery. And there's a chapter in the book specifically devoted to that. The thing to remember about these addresses is not to fear them, but to understand that they really are scoped for the local subnet. In other words, they do not go beyond routers. They are not registered in DNS, and they really have no other use other than to facilitate local subnet interaction. The next part of the address is a 64-bit interface identifier. There's a typo in this slide. It says interface index. My apologies for that. It should say 64-bit interface identifier. This is the last 64 bits of the address. And we can, which identifies that node on that subnet. Now we can create this interface identifier based on what's called an EUI64 address based on the MAC address. And if we have a 48-bit MAC address, we can translate that to a 64-bit EUI address. Or we can have what is called a randomly derived and permanent interface identifier to essentially mitigate anybody who's doing address scans on the subnet. So that defines the first 64 bits, and the interface identifier defines the last 64 bits. Okay, so that's the link local address. What is this router discovery process? Well, it's a pretty simple exchange of a router solicitation message sent by a host and a corresponding router advertisement message sent by a router. And sometimes they're multicast and sometimes they're unicast. It just depends on the state of the host. If the host is just starting up on the network, in a similar way that we send out these broadcast DHCP discover messages, we send out a broadcast router solicitation message. If we're already configured, we might send a unicast router solicitation. The received RAs that we get from our routers determine a whole bunch of interesting IPv6 configuration. They can determine these stateless addresses, these addresses that the hosts themselves configure and nobody really keeps track of. But we get the prefix from the router, the node adds an interface identifier, and we've got a non-link local address that we can use to get off the subnet. It also defines the on-link prefixes. What are the prefixes, or what are the routes corresponding to the local subnet? I need to add those to my routing table. Other configuration parameters like what is the default router so that I can create a default route on my routing table? What's the maximum transmission unit or MTU of the link? What are states of various timers and so on? And for our purposes, do I use a stateful addressing protocol, aka DHCPv6, to get stateful addresses, to just get settings from DHCPv6, or do I use it for both types of configuration? So let's take a look at this message exchange, see what's inside of these packets to give you an idea of some of the important elements of this interaction that informs the later auto configuration process. So here we have host A just starting up on the network. It hasn't even figured out whether its link local address is valid or not, and it's going to try to find a local router. So it sends out this multicast router solicitation message, and it's multicast because it doesn't have a unicast address, number one, and number two, it doesn't know which routers are on the network. So it sends it out to FF02:2, which is specifically defined link local scope all routers multicast address. All the routers are listening on that address, and they send back a corresponding, in this case, since host A has not yet configured its own link local address, the response is also multicast, so multicast router advertisement. Now inside of this router advertisement message is a whole bunch of interesting stuff. First thing to notice is in the IPv6 header, we're sending it to FF02:1, which is, again, a specially defined multicast address. In this case, the link local scope all hosts multicast address. So all of the hosts on the network are listening on this multicast address so that host A can receive it. If you look inside the router advertisement header, there's a whole bunch of stuff. Here's the current hop limit. Here's some timers. And here are two flags, the M and the O flag, that I'll define in the next slide, that tell you whether or not and how to use DHCPv6. The router lifetime field tells the host, if this is a non-zero value, that to consider this router, this advertising router, to be a default router for the amount of seconds in the value of the router lifetime field. There's also a priority field that allows routers to set relative levels of priority amongst themselves. So you can have a primary default router on the subnet and a secondary and so on. In the beyond the router advertisement header are a series of options where we advertise the link layer, or the MAC address of the advertising router, the MTU of the link. The prefix information options are where we're advertising, here's a 64 prefix that's relevant for this subnet. Inside of that prefix information option are two very important flags. There's an A flag that tells the host to go ahead and configure a stateless address. And then there's an onlink or OL flag that tells the host to go ahead and add a 64-bit route to their subnet for this local subnet route. The route information option is similar to the DHCPv4 classless static routes option, where we're actually advertising a series of routes to plumb in the routing table of the host. So lots of great information. What I want you to sort of focus on is the notion that, number one, the router is advertising itself as a default router using the router lifetime fields. There are a series of flags. The M and the O flag determine the DHCP behavior, and the flags within each prefix information option define how do I use that prefix. Do I use it to configure stateless addresses or add a local subnet route to my routing? Okay, so in this interaction, what are the relevant addressing elements for auto configuration? Well, number one, whether to configure a stateless address based on a given prefix information option. That's this A flag. I'm going to define it now as the autonomous flag in a given prefix information option. Whether to use DHCPv6 for stateful addresses. And this is the M flag in the RA header. This is known as a managed address configuration flag. This tells the host, use DHCPv6 to request addresses of a stateful addresses from a DHCPv6 server. And lastly, whether to use DHCPv6 for other types of configuration settings. And this is the O flag, also known as the other stateful configuration flag in the RA header. Okay, so that's the elements of auto configuration. There's also some routing information that's very important. Number one, whether to configure a local subnet prefix route for an advertised prefix. And this is this OL or onlink flag in the prefix information option. If this flag is not set, it's set to 0, or the prefix is not advertised, then I'm not going to add a local subnet route for that prefix. And that becomes very important a little bit later on as I'll discuss. Whether the advertising router is in fact a default router. Now notice I'm calling it a default router and not a default gateway. Default gateway is an unfortunate legacy term that we use in the IPv4 world. Going forward into IPv6, we refer to them as default routers. So is it a default router using this non-zero router lifetime field? What is its relative priority? And that router lifetime determines how long I can consider it to be a default router. And if that timer gets close to expiration, I may send another router solicitation to make sure it's still there. So I keep that default route in my routing table. And whether to add any additional specific routes to my file routing table, and this is that specific routes option in the RA message. Okay, so a lot of addressing stuff and some routing stuff all being done in the same message in the same RA that's being advertised by these routers. Okay, so let's look at these two flags, the M and the O flags. The managed address configuration flag that tells the host to use DHCP for addresses, and then the O flag, the other stateful configuration flag that tells the host to use DHCP to get configuration settings. If I clear both of these flags, and by clear I mean setting them to 0, this is basically corresponds to a network without a subnet, without a DHCP relay agent on it, or just a network in general without DHCP infrastructure. In this case, I'm not doing DHCP anything. I'm not doing stateful. I'm basically relying on the RAs and the prefix information options to configure non-link local addresses, like global addresses or unique local addresses. And I'm using other methods, manual configuration, or the information within the RA itself to configure other settings. And you think to yourself, well, what about DNS? What about this, that, and the other? One of the things to sort of get used to is the notion that when we talk about IPv6 migration, very typically, at least in the short term, we're talking about IPv6 in conjunction or in parallel to or as a dual stack on the same network. So IPv4 and IPv6 are working on the same network. And you still have DHCP for IPv4 providing those things like DNS domain names and the IP addresses of DNS servers and other types of settings. So those aren't being necessarily replaced by DHCPv6. And in some cases, you say, well, I just want the local routers to advertise the prefixes and let DHCPv4 handle all of the other configuration settings, and that's a perfectly valid way to go. Next one is both M and O flags are set. This corresponds to something called DHCPv6 Stateful, in the sense that DHCPv6 is providing complete addresses, complete 128-bit addresses, and in addition to that, any configuration settings like DNS domain name, DNS servers, and so on. And this corresponds to a situation where we want to use DHCPv6 to provide both sets of information, and maybe we don't want the routers to advertise local prefixes for stateless addresses, for example. The next combination is that the M flag is cleared, set to 0, and the O flag is set to 1. This corresponds to something called DHCPv6 stateless, where we're using stateless addresses as advertised by routers, but we're using the DHCPv6 server to provide configuration settings. Okay? So we're letting the routers do the addressing, and we're letting DHCP configure things like the IPv6 addresses of DNS servers, for example. The last one is the M flag is set, but the O flag is cleared. So we're using DHCPv6 for address configuration, but not for other settings. And this tends to be a somewhat unlikely combination, because if you're going to do DHCP for addresses, you're probably going to do DHCPv6 also for configuration settings like DNS and so on. So possible, but typically unlikely combination of M and O. So I wanted to pause here and point out some very interesting and key differences in IPv4 and IPv6 dynamic host configuration behavior, because it does take you a little bit by surprise, because you're so used to IPv4 and its host behavior and its DHCP behavior that I just want to take a moment to highlight these. First of all, there is no router equivalent to the router option in DHCPv6 to assign a default router. In DHCPv4, there's this router option, and you use it as a scope-specific option to configure the IPv4 address of the default gateway for that subnet. Well, there is no such router option defined in DHCPv6. In fact, IPv6 was designed so that the local routers are responsible for advertising themselves as default routers. Okay, so the default route, the default router, is only configured from the contents of the received RAs. Again, it's this non-zero router lifetime field in the RA header, and a combination of a priority field if you want to have a fault-tolerant configuration. Okay, so don't go looking for it in the list because it's not there. You have to have your routers advertise themselves as default routers using whatever set value of the router lifetime field. The second is that, unlike IPv4 hosts, IPv6 hosts don't automatically configure themselves with a local subnet route based on an address they receive from a DHCPv6 server. Okay, so in other words, if you want to dive into the details of DHCPv4, there's this subnet mask option that gets sent with the IPv4 addresses. And that subnet mask tells the IPv4 host between the allocated address and the subnet mask, add a local subnet route to your routing table corresponding to that combination. Well, there is no such behavior in IPv6. So that means in stateless mode, unless I also advertise the prefix using the RA, with the prefix information option, and tell the host to consider this an on-link prefix, I won't get a corresponding local subnet route in my routing table for that DHCP address. And this is sort of key. We want to make sure that we're getting the addressing information from one place and the routing information from another. And in fact, that is one of the key takeaways from this discussion, is that in the IPv4 world, DHCP is really assigning all of the addressing, all of the routing, and all of the additional configuration. It's all being done by the DHCP server itself, and the routers can sort of be considered as passive forwarding devices on those local subnets. In the case of IPv6, the routers are responsible for advertising the routing information, And DHCP is responsible for doing the addressing and the other configuration stuff. And what this does is it creates a point of collaboration, if you will, or disconnect, depending on how your IT department works. But in some IT departments, you have the router people over here, and you have the services people over there. The router people handle the routers, and the services people handle things like DNS and DHCP and so on and so forth. Well, in the IPv6 world, those two departments have to meet in the middle and agree on a particular configuration of not only router specifics, but DHCPv6 specifics, such that everything gets done, that the host is configured properly for all of the appropriate settings. Okay, so this is the way IPv6 was designed, and it is necessarily different in these ways from IPv4. And we'll see some consequences of that in some later slides. Okay, so one of the questions we get asked, or is sort of natural to gravitate to is, oh, okay, I'm not sure I quite understand all of this stuff, setting all these options and setting all these flags and so on. I know how my IPv4 auto-addressing configuration works and infrastructure works. Tell me how to do this in IPv6 so that's most like what I do in IPv4 with DHCP. Okay, so what is the most similar configuration? And herein, we say, okay, the routers are going to advertise the absolute minimum. They're going to be responsible primarily for the routing configuration of the host, the default gateway, the link local, the local subnet routes, any additional routes, and they're going to tell the hosts to use DHCP6 for everything else. So the routers are configured to advertise their presence and their length of time to be considered as a default router. Right? So that gives us our default route. They're going to advertise these local subnet prefixes with the OL flag set, the on-link flag set to 1, and the A flag, or the autonomous flag, cleared. The OL flag set to 1 means go ahead and create a local subnet route in my routing table. The A flag cleared means don't create a corresponding stateless address. Let DHCP do everything. And also set the M and O flags so that the host knows to do DHCPv6 stateful, so both addresses and configuration options. So, and then DHCPv6 will provide stateful address leases and any additional configuration settings like DNS, domain name, servers, and so on. So this is a configuration that is the most like IPv4, and you can see here it also exemplifies the fact that the routing department in an IT organization will need to handle that first bullet, and the services department handles the second bullet. And the two departments really need to meet in the middle to agree that this is the common configuration between the two to get the desired behavior. Okay, so if we're playing around on a Windows host, how do we set these address auto-configuration flags so that it does the right thing? And the reason I bring this up is that if you do the IPv6 Test Lab, you'll have some experience with this. But for the Windows router interfaces, and we're assuming that they're already configured to advertise, that they're configured to forward and advertise. They're acting as essentially IPv6 forwarders, and they're also advertising the presence of maybe a default router on the network. And they're also configured to publish certain routes relevant for those interfaces via the routing table entries. But beyond that, to enable DHCPv6 functionality, whether that's DHCPv6 stateful or DHCPv6 stateless, using a Windows router, to set the M flag in the outgoing RAs, you use the following command: net shell interface IPv6 set interface, identify the interface by its name or its interface index, and you set the managed address parameter to enabled. So that sets the M flag. And similarly, we set the O flag with the other stateful because enabled. And if you want to set both, you can do it on the same command line. But again, this is a way to set these flags on a given interface. So after these flags are set, the the next RAs that are sent out have these two flags set, and now the hosts see those flags, and they automatically use DHCPv6 to do the additional DHCP configuration. Okay, so what about third-party routers? I mentioned the previous one just because if you're playing around in a test lab, playing around in the IPv6 test lab, for example, you'll have some experience with these options. But in the real world, on the real network, chances are you're using an enterprise router, a Cisco, F5 network, Juniper, whatever. And what you need to be able to do is understand what flag I need to set on those third-party routers. And here we have for just stateless address auto-configuration, which means no DHCPv6. We need to configure those routers that on an individual interface and subnet basis to go ahead and clear both the M and the O flags in the RA header. And this is probably the default. So don't tell the host to do anything with DHCPv6. Don't use a stateful address auto-configuration protocol to do anything beyond what's already being advertised. And in the prefix information options themselves, again, the prefix information options are typically advertising a 64-bit subnet prefix or a global prefix or a unique local prefix. And go ahead and set both of those flags. By setting both of those flags, the OL flag creates the local subnet route in the routing table, and the A flag ensures that the host creates a stateless address auto-configuration address. For DHCPv6 stateful, where we're using DHCP not only for addresses but additional configuration settings, I'll go ahead and set both of those M and O flags in the RA header. And in prefix information options, set the OL flag so that the host configures the local subnet route, and clear the A flag so that it does not create a stateless address based on that. For DHCPv6 stateless, set the O flag. Okay, so we're saying use DHCPv6 for other configuration, but clear the N flag. Don't use DHCPv6 for addresses, and then set both the OL and A flags in the prefix information option. So we're getting all of our addresses through our RAs, and we're just getting additional configuration settings through DHCPv6. Okay, so that's a summary of those 4 flags, and not only RA header but prefix information options for the 3 sort of common configurations you might have out there. And these typical high-end routers have the flexibility to do all of these things. Now here's something that's interesting with Windows-based IPv6 routers, and you'll encounter this in the test lab if you go through it, is that we don't have an option, or we don't have a net shell option when we add the routing table and configure it to be published, to clear the A flag, the autonomous flag, which means that anytime we create a route, put it in our routing table, and configure it to be published, it's going to set both OL and A flags. So it's going to configure a local subnet route, and it's going to configure a stateless address based on that. Now, what this means is that if you use a Windows-based IPv6 router as your advertising router, and you do DHCPv6 on top of that, there are really 2 results that you might get if you do DHCPv6 stateful, which is even all flags are set. If you don't advertise the prefix, tell the router don't advertise this particular prefix, and you rely on DHCPv6 for all configuration, it's going to configure that single stateful address through DHCPv6. However, because the host does not automatically add a 64-bit route based on the address received from DHCPv6, there is no local subnet route in the routing table. So that's interesting, and that's totally expected behavior. Remember that in IPv6, the routers are primarily responsible for advertising the routing information, and DHCP is really designed to do the individual address and other configuration settings. What this means is that hosts on the same subnet that want to talk to each other and want to communicate to each other using one of those relevant non-linked local addresses will first send it to the router, and then the router does a redirect function, and then subsequent packets will be sent between the 2. What it means is that it prompts a redirect situation, and there's you could argue that it's relatively inefficient. It adds host routes. If there's a lot of intra-subnet communication, let's say servers in a data center or something, it could have an effect on network performance. And in some cases, people turn off redirects, so that would totally break. So this is just the nature of using a Windows-based IPv6 router, and I'll come back and caveat the whole thing in just a second. So that's one result. Don't advertise the prefix. You just use DHCPv6. I get a single address, but no corresponding local subnet route and corresponding redirect situation. Or I can do DHCPv6 address configuration with an advertised prefix, in which case I get two addresses. One that's stateless, advertised through the RA, because when Windows advertises an RA, the A flag is always set, and one through DHCPv6. The good point is that because I advertise it through the RA, the OL flag in the RA is also set, and I get a local subnet route in the routing table. In other words, no redirects for local subnet traffic. Now, if you're using a Windows-based router, like in the test lab, the second option is really the most recommended, just because you don't have this redirect situation, and you have, consequently, a stateless address advertised through the RA and a stateful address advertised through DHCP. Now, how terrible is this? Well, it's not, again, it's not terrible, because in the real world on the production network, you're probably going to use a routing device, Cisco, F5, Juniper, et cetera, and they don't have this particular configuration issue. But I bring it up because if you do the test lab, you'll sort of run into this particular configuration anomaly, and it's all just because there's no way to clear that A flag. If we had the ability to clear the A flag, we could do DHCP stateful and have a single address per host on DHCP. Okay, let's move on and talk about the DHCPv6 protocol in general, and then talk about some Windows configuration and general deployment configurations. So DHCPv6 was sort of designed to be equivalent to DHCP for IPv4. Again, there's a typo here. I apologize. Take a look at RC 3315. They took all of the sort of best things of DHCP for IPv4 and created a new protocol that works pretty much the same way. What sort of DHCPv6 infrastructure do I need? Well, it's the same as DHCP4. You need clients, you need servers, and you need relay agents. And I've noted here the versions of Windows that support a DHCP client, that support DHCPv6 server, and have included relay agents. And you utilize these, again, if you do the IPv6 test lab. But it's really quite the same thing. You're configuring additional components on routers to do the relay function, and you've got a central bank of DHCP servers that in many cases do not only IPv4 address scopes, but also IPv6 address scopes. So what does this protocol look like? Well, it's UDP over, you guessed it, IPv6 as opposed to UDP over IPv4, which would make a whole lot of sense. But the clients listen on UDP port 546, and the relay agents and servers listen on 547 in a similar way that DHCP does. And another interesting contrast is that DHCPv4 uses this limited broadcast and corresponding MAC broadcast when it doesn't know where anything is. And of course, in IPv6, there is no such thing as a broadcast address. So in this initial interaction, just starting up on the network, DHCPv6 will use multicast addresses, and specifically a well-defined reserved address, FF02:1:2, which is reserved for DHCPv6 servers and relay agents. They're listening on this particular address, and when clients wake up and want to do what's called a solicit message to find where the relay agents and servers are and ask for address configuration or configuration parameters, it sends to that address. They're listening to that address, and they take that multicast message and they turn it into the unicast to forward between the relay agents and servers. And again, it's a very similar fashion as DHCP4. So here's just a quick little diagram. The client is multicasting certain messages in its initial configuration, and the relay agent and the server are exchanging unicast messages. Okay. Let's take a quick look at the stateful message exchange. Again, both the M and the O flags are set, so the client is not only asking for addresses, but it's also asking for additional configuration parameters, other configuration settings. So the first thing it does, again, assuming that it's just waking up on the network, it's going to send this multicast solicit message and to locate the servers. And typically, it's going to be picked up by a relay agent on that subnet, and that solicit message will be bundled up and unicast to a DHCPv6 server. The solicit message is, of course, equivalent to the DHCP discovered every hour from DHCP for IPv4. The response to that is an advertised message, equivalent to the offer, and the server relays it back to the relay, and the relay sends it as typically a unicast message to the link local address of the host that's trying to use DHCPv6. And then the DHCPv6 host sends a multicast request message, and this is the saying, okay, out of all the offers, I choose this one. Please, server who offered this, offer it back, and inform the others that it's not interested in the releases that they offered. And again, much the same way as DHCP for IPv4. This is equivalent to the DHCP request. And then the corresponding reply, equivalent to the ACK, contains the addresses and other configurations. So simple for message exchange, very similar to DHCP for IPv4, does the whole stateful stuff. Now for stateless, here's where the M flag is cleared and the O flag is set. We just want configuration parameters, then we send multicast information request. This is equivalent to the DHCP form. Hey, I want these, give me these DHCP6 options, and then the reply, once again, provides those options. All right. So this flowchart sort of summarizes at a fairly, well, not down to the packet level and flag level necessarily, but it sort of summarizes the overall process of auto configuration for IPv6. A host wakes up, sends a router solicitation, and hopefully receives them. If it doesn't, it falls back to using DHCPv6 stateful. It sends out a solicit message, essentially. If there are router advertisements received, it sets those configuration parameters like the hop limit, timers, and MQ, and so on. Sets the default route if advertised. And then it looks to see if there are any prefix information options with the A flag set. Okay. So if the A flag, the autonomous flag, says configure a stateless address, and if it receives them with the A flag set, it goes ahead and configures those stateless addresses. If the A flags are not set, or we've done configuring stateless addresses, we see if the M or O flags are set. And if the M flag is set, or the M and O flags are set, we do DHCP stateful. If just the O flag is set, we do DHCP6 stateless. And then once that is done, then we're done with address auto configuration. And we can proceed with other network startup processes. What I wanted to show here is the path that would be taken by an infrastructure that is, again, most similar to DHCP with IPv4. In other words, we configured our routers to advertise prefixes, but to clear the A flag, and we're setting both the M and the O flag. So we go through the flowchart, and we bypass the configure stateless addresses, and then we take the path of let's use DHCPv6 for everything that we can. Okay. So how do we do this with Windows? Well, we've got DHCPv6 clients in Windows Vista and later. There's nothing to configure. It's going to do the behavior that we saw on the previous slide and just operate like a RFC compliant IPv6 host relative to DHCPv6. Okay? So just put the clients on the network. In other words, there's no flags that configure. It's just built in. With DHCPv6 relay agents, we need to configure probably our existing routers with agents or helpers or whatever they're called that have equivalent functionality to DHCP relay agents. when we're configuring a relay agent, we typically have a couple of things to do. We have to tell the router which interfaces to act as relay on, and we need to configure the router with the unicast addresses of the DHCPv6 servers. So we're putting in IPv6 addresses, or there may be some timer and priority information as well. But those are the two key things. On which interfaces on the router am I listening for DHCPv6 traffic and acting as a relay on? And number two, where do I relay those messages to the DHCPv6 servers? You can use the routing remote access service in Windows Server 2008 and later to add a relay agent to a network. But very typically, you're going to use your existing portfolio. What about DHCPv6 servers? Well, on your servers, very typically, at least nowadays, you can configure address scopes and options, IPv4 address scopes and options, and now IPv6 address scopes and options. So create a scope for each subnet that is supporting native IPv6 addressing, either global address prefixes or global address prefixes. You can create exclusions, you can create reservations, you can create router and scope and node-specific options as well in a very similar manner that you do with DHCP4. Okay, so what does DHCPv6 look like in Server 2008 and R2? It's built into the service, but note that there are no superscopes or multicast scopes as yet. This is a hard requirement. Just like DHCPv4, you need to configure a static IPv6 address on each interface on which it is going to be listening for DHCPv6 traffic. So you make up a static address and you assign it to the interface of the server. And there's this IPv6 node in the DHCPv6 snap, and I hope you can see that. But basically, it has a very similar structure as the IPv4. So I encourage you, again, in the test lab, you can do this directly yourself. Now, one of the things that comes up when you install the DHCP server role in 2008 and R2 is during the wizard, you get this page that says configure DHCPv6 stateless mode. And admittedly, it's a little confusing and maybe a little bit misleading because there's an option to enable stateless DHCPv6 stateless or disable DHCPv6 stateless. All this is really doing in this page in the wizard is deciding whether or not to prompt you with an additional page called IPv6 DNS settings. If you enable stateless mode, it prompts you for the IPv6 addresses of DNS servers. If you disable it, it doesn't. But in no way does this wizard disable the functionality of the DHCPv6 component of the DHCPv6 server service to provide either stateful or stateless after the wizard is run. So what the wizard is trying to do is make it very easy for you to do DHCPv6 stateless by prompting you for an additional page for the IPv6 addresses of DNS servers. After the wizard is done, you can basically do whatever you want with DHCPv6 via the DHCP console windows. Okay, well, what about the relay agent? Well, again, it's a component of the routing remote access service in Wizard. So in Windows, you add the routing remote access service, and then you go to the IPv6 general node, you add a routing protocol. There's a DHCP6 relay agent component. You add that. You configure the IPv6 addresses of the DHCP6 servers, where to relay the messages, and then you also add a series of interfaces. These are the interfaces on which to listen. And again, it's very similar to any other relay agent in terms of saying what interfaces are you listening on and where do you want to relay the traffic to. Very straightforward. Okay, so some general DHCP6 deployment considerations. Yes, you are creating, managing, and maintaining a parallel address allocation infrastructure. You're doing DHCP and DHCPv6. So theoretically, every subnet has a v4 scope and a v6 scope and their corresponding options and the corresponding router configuration for IPv6 that matches. And that's a conscious decision you're going to have to make to say, you know, I need DHCPv6 for these reasons, and I'm going to go ahead and take the hit to maintain this parallel addressing infrastructure. You're doubling the load on your DHCP servers because each client now is going to use both DHCP for v4 and DHCPv6, so it's going to be hitting the servers relative to the leak times. Is this a huge consideration? If you have a DHCP server that's close to being maxed out, you probably don't want to do DHCPv6 on it, or maybe move to another server, for example. You're also doubling the traffic on the network. You're doubling the DHCP traffic on the network. Very typically, and I'm pulling this out of the air, your DHCP traffic is 0.002% of your overall traffic, so now you're using 0.004% of your overall traffic. I'm being a little facetious here, but it's really not that big of a hit with the types of bandwidths and pipes that we have now. And you have to figure out who's going to be the relay agents on each one of these subnets. I need to configure at least one. Okay, so here's an interesting issue with Windows-based hosts and the use of secure dynamic update and non-domain members. Secure dynamic update is something I configure on my DNS zones to say, I need some credentials in order to add this address record to keep people from spoofing and things of that nature. Well, with domain members, that's not a problem. The domain members will provide the credentials to automatically or dynamically register their address, their A records for IPv4, and their quad A records for IPv6. No problem. Non-domain members will rely on the DHCP server to register them on their behalf. So there's a DNS tab on the properties of a scope. You say, go ahead and register on behalf of the clients. But that's if you're using DHCPv6. Now here's where it gets interesting. If you're using non-domain members and they're doing just stateless address auto-configuration, they'll get their A records registered because they're using DHCP and the DHCP server is registering their records on their behalf, but their quad A records corresponding to their stateless IPv6 addresses are not being registered because they can't, because they don't have credentials, because the DHCPv6 server is not involved in doing this on their behalf. So it's an interesting sort of disconnect in the sense that the domain members can get all their quad A records registered. The non-domain members of DHCPv6 can get their quad A records, but the non-domain members that are using stateless address auto-configuration cannot. And the solution there is to do DHCPv6 on those subnets that contain those non-domain members. So, real quick recap. Why would I want to use DHCPv6? Well, for all the reasons I use DHCP4, which is not just ease of administration, but I want to know who had what IPv4 address and for how long and when, because I may not want to do tracking or forensics or analysis. This is an important thing. And with DHCPv6, I have that for IPv6, whereas when I'm doing stateless and just letting the routers do RAs, I don't have that ability. I want to use DNS traffic over IPv6. The only way to do DNS traffic over IPv6 is to configure the hosts with the IPv6 addresses of DNS servers, and I can't do that through DHCP for IPv4. I can manually configure them, but it's much, much easier, obviously, with DHCPv6. And lastly, to address this issue of non-domain joined hosts being able to register their quad A records for DNS dynamic updates and secure dynamic updates. So 3 good reasons for using these. Okay, what I wanted to do in this last slide is to just introduce you to this notion of the IPv6 Test Lab. The IPv6 Test Lab is part of the overall Test Lab Guide initiative that I've been driving at Microsoft, across Microsoft, to set you up with a standardized Test Lab environment and a set of modular documents to build out and demonstrate technologies, products, and even multi-product end-to-end solutions. And so there's a portal page out there on the TechNet Wiki that describes the set of documents for IPv6 Test Lab. There's a Demonstrate IPv6 Test Lab guide that takes you through link local, ISOTAP transition, and then finally native IPv6 addressing. And then there are a series of extensions that take you through DHCPv6 and actually converting the little subnet, the little corporation intranet to an IPv6 only Test Lab extension. And so I encourage you, if you're just starting out with IPv6, to access these resources and build out your test lab. use Network Monitor, whatever network sniffer to analyze the traffic and really have a solid test bed to test and play with IPv6. This is also, this documentation exists from this wiki page, but is also built into the Understanding IPv6 3rd edition book using via Appendix C, which is a customized version of all of this information. So with that, I'm going to go and skip the demo, and for the remaining minutes, we'll take some Q&A. Okay, Yasmina, do you want to moderate the questions, or do I just?
Sure, let's do it. All right, we'll take them in the order they came in. We have a question from Ahmad. Ahmad says, can Windows Server 2008 function as a IPv6 router that is able to send out router advertisements?
Yes. With the understanding of what I mentioned, which is they can send RAs, but one of the sort of anomalies is that if it's advertising prefix information options, it advertises them with both the OL and A flag set, which means you're always going to get a stateful address configuration based on that sent RA. And the way to configure that is you can just query on configure IPv6 router in a search window, or you can go to the test lab documents and see the command lines there.
Great, thank you. Our next question here, let's take a peek, is from Egan. Egan says, in real life, is there a scenario where an IPv6 address isn't a 6.4 address?
Isn't a 6.4, I mean the 6 to 4 address?
/6.4. Sorry, maybe I'm not saying it right.
Okay, let me try to find the question. Oh, I see. Okay, is there a scenario where an IPv6 address isn't a 64-bit address? Okay. Yes, but they're not necessarily recommended, and very typically you see those /127 types of addresses on point-to-point WAN links between two routers, and the reasoning there is they don't want to use up an entire 64 prefix for two addresses, so they'll assign a /128 and manually address the endpoints. In DHCP and your typical subnet, IPv6 has been designed to do this sort of 50-50 allocation between 64 bits of subnet and 64 bits of interface identifier. So to answer your question, there are sort of corner case scenarios, but the very typical subnets, you're going to end up with a 64-bit address.
Thank you. Another question here. Does the router advertise who the DHCPv6 server is, like DNS name or IP?
No, it does not. All the advertising router does is through the M and the O flags indicate to the host whether or not to use DHCP for addresses or other configuration settings, or for both. It's the DHCPv6 relay agent that is where you configure which IP addresses to send to relay the messages back to the DHCPv6 server. So to answer your question, no, that's really a function of the relay, the DHCPv6 relay agent.
Thank you. Another question here. How is a Windows interface set to send out RAs?
Okay. So you remember the netshell interface IPv6 set interface command that we used to set the M and the O flags? Well, there are some additional options there. Netshell interface IPv6 set interface, the interface name or identifier, and then you say forwarding equals enabled if you want it to be a forwarding interface, and advertise equals enabled if you want it to advertise as an advertising router on that interface. So it's some additional options. Forwarding equals enabled, and then advertising equals enabled, and you don't need to use those at the same time. For example, you can have some routers that are devoted to forwarding and other routers that are devoted to advertising prefixes and so on.
Great, thanks, Joe. All right, another question here from Ilya. Does NATv6 or some kind of IPv6 address translation exist?
Yes, there is a NAT64, DNS64 component that allows an inbound IPv6 packet and address to be translated to a corresponding IPv4 address and IPv4 packets. And this is a capability that we have for direct access in our current Unified Access Gateway product that is now being supported by Windows Server 8. So yes, it's address translation as well as packet translation to allow an IPv6 host an IPv6 only host to communicate with an IPv4 only host across this device.
Wonderful. And our last question here looks like it's from Tracy. Tracy asks, what if our Windows domain does not allow self-registration of an address at all?
Then you're saying your hosts don't allow the computers to register their IPv6 to register with DNS. Well, then it's sort of a non-issue in the sense that, and I guess I'm not sure why that would be, because with DHCP you want the host to always register its current IPv4 address so that people can resolve its name. I'm not quite sure how to answer that question. If it doesn't allow self-registration of addresses at all, then neither A records or quad A records will be registered either by the host or on behalf of the DHCP service.
Okay. Looks like Tracy replied with DHCP is handled outside the domain currently, but the hosts are in the domain.
Okay.
If that helps clarify a little bit.
A little bit.
Okay. Perhaps I was going to say, perhaps Joe will give some information on how you folks can contact him and follow up a little bit later on offline. I'm sure he'd be happy to, answer any additional questions. So
I think I'd have to investigate that particular question a little bit more in terms of, sounds like the DHCP servers are not members of the domain and therefore can't register on behalf of clients. And in that case, your non-domain members won't be able to register either IPv4 or IPv6 addresses in DNS. It's a bit of a moot point, if I understand the information.
All right. I'm not seeing any additional questions coming in, Joe. So is there anything you'd like to leave our attendees with today?
Well, I would encourage them to, this is an important area of IPv6, and I think something that people will naturally gravitate to initially because they're concerned with, okay, I need to do IPv6. The first thing I need to do is figure out how to get it on my network and do it gracefully and do it with a minimal pain. And so this area of understanding the host behavior relative to auto-configuration, the router behavior, and the DHCPv6 relay agent and server behavior relative to address auto-configuration, I think goes a long way to getting native IPv6 infrastructure up and running and running the way you want and behaving the way you want. And then you can look at how that native infrastructure is being used by your applications. So I think this is an important topic as a first step to figuring out how to deploy a native IPv6 infrastructure across your network. Great. And I would encourage you very much, if you haven't already, to set up a test lab and play with it, or use the IPv6 Test Lab documents that are referenced here, or Appendix C of the 3rd edition book, in order to step through that and gain that hands-on understanding of what's going on.
Joe, thank you so much for presenting such an outstanding webcast for us all today.